Section 35 of The Science History of the Universe, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. The Science History of the Universe, Volume 1, edited by Francis Rolt Wheeler. Astronomy. Chapter 23, Variable and Binary Stars, Part 2. Powerful spectroscopes are now able not only to resolve what appears as one point into two, but to detect motions of the two suns around their gravitation center. This has been simply explained by Professor Larkin. He states that by the application of Doppler's principle, the times of revolution can be observed, and when the distant suns have a sensible parallax, the distance between them can be determined in miles. With time and distances known, velocities in their orbits follow at once. Then, with velocity and distance, the mass of both can be computed. That is, both suns can be "weighed" in terms of the mass of our sun. For it is known from the laws of gravity and motion how much matter is required at any given distance and velocity to set up centrifugal tendency equal and opposite to gravitation. The Doppler principle applied to the discovery of binaries is shown in the diagram, where S is a sun far and away to one side of the center of the orbit of its companion as shown in four positions A, C, P, G. As seen from the Earth, when at G, the flying sun will send fewer waves per second into the spectroscope and the Fraunhofer lines will shift toward the red. The point A is apastron and P periastron. The velocity of the revolving sun at P in its orbit is enormous, while the light and heat of S are intolerable to the people on any planet revolving around the sun P. For if either sun has a retinue of worlds like the Earth, with inhabitants, their changes of climate are extreme. While the flying sun is moving from A through C and around to P, the huge sun S rapidly increases its apparent diameter and also its light and heat. After passing C in the direction of the arrows, S must look like a blazing globe in skies of incandescent brass. In the revolution of a planet around either sun, it would move in between them. There would be no night. The world and its people would be between two white-hot suns. Life would expire. But if by chance a few of the inhabitants survived the passage through P, they would freeze when their sun reached the distant point A. Therefore all binaries having great eccentricity of orbits are utterly worthless for support of life on their planets, if they have any. All planets are invisible from space, whence it follows that the inhabitants of stellar spaces have not heard of the Earth. Let us try Kepler's third law on a binary. Suppose an astrophysicist on this speck of dust, the Earth, far away in the direction of the arrows, say 100 or 200 trillion miles, it makes no difference which, provided the light from the stars reaches the Earth in quantity sufficient to form a spectrum whose lines can be measured, wishes to find out how much matter the two suns in the diagram contain. He sets the telespectroscope on the pair night after night and measures with extreme accuracy the shifting of the lines, now toward the red and then the violet. He does not see the stars in the instrument but their spectra only, tiny delicate and beautiful bands made up of a few colors and black bands. But he watches the lines with great care when the moving sun is at C and G and measures their displacement with the micrometer. By repeated observations he finally learns a thing of vast import: the speed of the sun's revolution in its orbit, and this entirely by means of the known relation between shifting of spectral lines and the speeds of the flying sun at times of approach and recession. And by direct observation he notes the time of one revolution. He multiplies velocities per second by the number of seconds and thus finds the circumference and radius of the orbit. He at once knows how many times farther apart the two suns are than our sun and Earth. Then it becomes simple arithmetic to apply Kepler's law and find mass. The distribution of the stars in the heavens seemed to the ancients to be fairly even on the whole. It was noted, however, that there was a long, relatively thin segment of space extending across the sky in which the stars appeared more numerous than elsewhere, and on account of its brilliancy this was termed the Milky Way. Aristotle discusses it among other astronomical phenomena, and Greek astronomers looked upon it as a great circle of the celestial sphere. From these days to the present no satisfactory explanation has been offered for the existence of such a segment with the Earth apparently at its center, nor indeed for any of its characteristic peculiarities of aspect and its relationship to the stellar universe. Galileo, with his telescope, found that portions of the Milky Way consisted of multitudes of faint stars clustered together. It was recognized that the stars in the heavens were more and more closely massed as the Milky Way was approached. With the realization that all stars were not at the same distance, there naturally followed speculation as regards their arrangement and distribution. The first positive contribution to the various theories and the apparent distribution of the stars in space came from Thomas Wright, of Durham (1711 1786), published in his Theory of the Universe (1750). This theory is of interest not so much in its original form as propounded by Wright, but for the fact that it was taken up 5 years later by the great philosopher, Kant, and by him developed into philosophically explaining the origin of the universe. Furthermore, in the hands of Sir William Herschel it became an important astronomical theory which received serious consideration for many years. Herschel's hypothesis was that the space occupied by the stars resembled in form a thick disk or grindstone close to the central part of which the solar system was situated. When such a disk was looked through lengthwise more stars were seen naturally than when it was looked through breadthwise. But at the same time there were vacant spaces or holes in the groundwork of the Milky Way so that we can apparently see through the collection of stars. These holes or clefts are difficult to explain. The Milky Way has been described by Professor George C. Comstock as "a belt approximately following a great circle of the sky, but broad and diffuse throughout one half of its course, while relatively narrow and well defined on the opposite side." The broad half of the belt is cleft in two by a dark lane running along its axis, and in addition contains numerous rifts and holes, from which the narrow half is relatively free. The number of stars per unit area of the sky is a maximum in the Milky Way and diminishes progressively on either hand, while the inverse relation is true for the nebulae, their frequency increasing with increasing distance from the Milky Way. But even the most superficial observer is forced to the conclusion that the stellar system is of limited extent and does not extend to an infinite distance. For if stars and suns exist through an unlimited space, their luminous radiations, which do not suffer in intensity in their passage through the ether, would reach the known universe with little diminution, and the entire heavens would always blaze with light. That such is not the case is known from experience and from the fact that the combined illumination furnished by all the stars is only about 1/100th part of that obtained from the full Moon. The theory has been advanced that the dark holes in the Milky Way, coal sacks as they have been termed, consist merely of dark stars or extinguished suns, such as the one we have seen occasions the eclipse of Algol. But this was disputed by the late Professor Newcomb, who says that there is no evidence that the light from the stars in the Milky Way, which are apparently the most distant bodies visible from the Earth, can be intercepted by dark bodies or dark matter, and that the stars are seen just as they are distributed in space. Furthermore, recent photographic work indicates that there is a limit to stellar distribution and that there is a darkness behind the stars which long exposure and powerful instruments cannot pierce. The problem is one of striking immensity. Professor E. C. Pickering speaks of the distribution of the stars and the constitution of the stellar universe as perhaps the greatest problem in astronomy. In a recent discussion he remarks, "No one can look at the heavens and see such clusters as the Pleiades, Hyades, and Coma Berenices without being convinced that the distribution is not due to chance. This view is strengthened by the clusters and doubles seen in even a small telescope. We also see at once that the stars must be of different sizes, and that the faint stars are not necessarily the most distant. If the number of stars were infinite and distributed according to the laws of chance throughout the infinite and empty space, the background of the sky would be as bright as the surface of the Sun. This is far from being the case. While we can thus draw general conclusions, but little definite information can be obtained without accurate quantitative measures, and this is one of the greatest objects of stellar photometry. If we consider two spheres, with the Sun as a common center and one having 10 times the radius of the other, the volume of the first would be 1,000 times as great as that of the second. It will, therefore, contain 1,000 times as many stars. but the most distant stars in the first sphere would be 10 times as far off as those in the second sphere, and accordingly, if equally bright, would appear to have only 1/100th part of that apparent brightness. Expressed in stellar magnitudes, they would be 5 magnitudes fainter. In reality the total number of stars of the fifth magnitude and brightness is about 1,500, of the 10th magnitude 373,000, instead of 1.5 million as we should expect. An absorbing medium in space which would dim the light of the more distant stars is a possible explanation, but this hypothesis does not agree with the actual figures. An examination of the number of adjacent stars shows that it is far in excess of what would be expected if the stars were distributed by chance. Of the 3,000 double stars in the Mensuræ Micrometricæ, the number of stars optically double, or of those which happen to be in line, according to the theory of probabilities, is only about 40. This fact should be recognized in any conclusion regarding the motions of the fixed stars based upon measures of their position with regard to adjacent bright stars. End of section 35.